Hello, judges. My name is Max.
And my name is Damalati.
The title of our science fair project this year is called Blown Away. Our title, Blown Away, refers to how the wind blows on a wind turbine and how a turbine harnesses the kinetic energy of a wind to produce electrical energy. We also thought it was a somewhat catchy and creative title. Just before we get started, there are a few terms we would like to explain just to clear the air. If we mention RPM, we were referring to the revolutions per minute of the turbine's rotor, and if we mention gear ratio, we were referring to the gear ratios of the turbine, in which there are three. Also, when we refer to a traditional blade design, we are referring to the blade design made up of the long white blades with a traditional tapered design. And when we refer to the short blades, we are referring to the shorter blue blades you can see on screen right now. The reason that we chose this project was because last year we had a project where we tested the aerodynamic characteristics of aircraft wings inside of a wind tunnel, and this year we wanted to build off of it without continuing the exact same project. We chose to study the design of wind turbines this year because they are a clean source of renewable energy and will most definitely become a big part of our future. To start off, we first assembled our wind turbine. We went through the trial and error stage until we found the design with the least amount of shaking, and that was the most stable design. We came up with a wooden design that compensated for the shake of the original plastic design of the wind turbine, as you can see on screen right now. After that, we set up the fan 1 meter away from the wind turbine, which we found out was the optimal distance. From there, we set up our anemometers and took an average recording for all three fan speeds. After that was done, we started with our voltage recordings. The way we did this was we let the wind turbine run on the set gear ratio and blade angle for 120 seconds, or 2 minutes, taking a recording every 10 seconds and divided them to create an average. You can see this example on screen right now. We started recording on fan speed 1, moving from the traditional 3-bladed design to the short 2-bladed design, then to the short 3-bladed design, and finally the short 6-bladed design. We changed the gear ratios and the blade angles along the way. We repeated this process multiple times for fan speed 2 and fan speed 3.
Looking at the first gear ratio, 1 to 1, we observed that on the traditional 3-bladed design, as the blade angle increased, the amount of voltage produced decreased. Looking at the short 2-bladed design, we discovered that the only fan speed that actually spun or produced a consistent voltage was fan speed 3, which makes sense since there are only 2 shorter blades barely producing a strong lift force. On the short 3-bladed design, across all fan presets, you can see the amount of voltage produced steadily increases as the blade angle increases, which was expected. We can see the same trend on the 6-bladed design as well. We can also see that the 6-bladed design produces the amount of voltage consistently on gear ratio 1 to 1 as we predicted in our hypothesis. On the 1 to 3 ratio, we can see that on the traditional 3-bladed design, voltage production becomes lower and lower as the blade angle increases. And on the 30-degree angle, we can see that no fan speed is able to produce sufficient voltage. In terms of the short 2 and 3-bladed designs, we can clearly see that no fan preset was able to generate a voltage. This does indeed make sense as the 1 to 3 gear ratio takes the most kinetic energy to rotate. The short 6-bladed design was the design that produced the most voltage. Looking at the 3 to 1 ratio, which is here, we can see that for the traditional 3-bladed design on fan speed 1 and 2, voltage decreases when the blade angle increases as expected, but an anomaly that we saw was that on fan speed 3, the voltage actually increased as the blade angle increased. We weren't quite sure as to why this happened, but then we realized that it was a 3 to 1 ratio, the ratio that requires the least amount of kinetic energy to rotate, meaning that the rotor would likely spin at a much higher RPM. Since fan speed 3 produces strong gusts of wind, blade angle became less relevant, as all blade angles produce a similar RPM. On the 3 to 1 ratio, the short 2-bladed design produced voltage as expected, but we see some interesting trends when it comes to the short 3 and 6-bladed designs. We actually see voltage peak at 20 degrees, then decrease towards 30 degrees. We think that occurred because once the rotor reached its maximum efficient RPM, which was about 180 RPM for the 3-bladed design and about 200 RPM for the 6-bladed design, the amount of drag produced by the turbine's blade was equal to the force of lift, so the RPM actually decreased.
There were definitely some difficult parts of our project. By far the largest source of error that was the most difficult to solve was the shaking of the wind turbine and the random stalls of the rotor. We figured out that the shaking of the wind turbine was because of the turbulence produced by the fan, and the stalls occurred because of uneven amounts of air pressure that were exerted on the rotor's blades at certain times. In this video, you can see me shaking the wind turbine prior to our wooden design. We figured out that those were two sources of air that would never completely disappear, but we were able to mostly overcome them. How we countered the shaking of the wind turbine was by using three aluminum rods and fixing one end to the rod to the nacelle and the other end to the base of the wind turbine. To conquer the randomly occurring stalls, we figured out that the best distance was to keep the fan 1 meter away from the wind turbine. We also left the door to the living room open, where the wind turbine was set up, to create a draft and even out unwanted back pressure created by the fan.
Some things we enjoyed about our project was the fact that we got the opportunity to further develop our knowledge about wind turbines, all while working with a downscale model of an actual turbine. The ability to get hands-on with a wind turbine and see how they really function was something that we enjoyed. We also somewhat enjoyed the science fair experience, as painful as it can be sometimes. It really is an experience that sets us up for high school research projects, and it thoroughly teaches us how to cope with stress in times when we have a lot of work to do. The science aspect certainly is important, but the overall experience is something that can be utilized outside of our science fair projects.
In terms of continuing research to our project, a couple of things could be done. A major area that we wanted to research, but weren't able to given how much time we had, would be to learn the Arduino language. Arduino is a software similar to that of Raspberry Pi, which is a miniature operating system and can be used for countless projects. In our case, we would have utilized Arduino to create a fast and accurate tachometer that could insert RPM readings straight into an Excel spreadsheet for us and take out the hassle of us manually doing so. The same goes for our voltage recordings. Arduino is very vast and only mildly complicated, so if we were aware of it before the project, we would have been able to utilize it to capture more accurate results. Something else that we could have done in terms of further research on our project would be to design and print our own blades for the wind turbine. We were actually able to design our own blades via Tinkercad, which is a computer assisted design software, and design them based on the airfoil from last year's project, the deep camber airfoil, which actually performed best from low to mid speeds due to its unique curvature. We underestimated some of the timing on this project, and so we were unable to print off the different blades. But regardless of that aspect, we were still able to generate some promising results that both, in a way, supported our hypothesis and satisfied us as well.
The duration of our science fair project this year took place at Max's house, where the wind turbine was assembled where the final test bed was constructed. All of the experiments happened in the living room of his house, an open area that did not restrict airflow. We would also like to thank my dad and Max's dad for their support on this project. They were able to help us source all the components we needed to complete our project, and they also helped us with the assembly of our test bed. We are deeply grateful for their support and grateful that they always pushed us to do the very best we could. Thank you very much to all the judges that gave up their time in order to judge an online science fair this year. We understand that COVID has made presenting our project a bit more challenging than usual and a bit more difficult to judge, but nonetheless, we appreciate your patience throughout the process. We hope that we can see everyone in person next year, and remember to stay safe during these times. Goodbye.
Goodbye.